In the last video, we used a timer counter interrupt to toggle a LED at a specific frequency. If, however, we were more interested in the specific amount of time that the LED was on versus off, we would look at pulse width modulation, based on the principle that the current through a pin is directly proportional to the percentage of time it's on versus off, and so can be used to finally control current to, for instance, DC motors in control environments. Now, for pulse width modulation, you want a very high base frequency. That's the kind of a short period over which you are measuring and modulating the on versus off time. But you also want a higher resolution so that you can finally control the amount of current going through the pin. So we're going to use the AVR timers to generate some PWM and modify the solution that we had last time so that we are able to dim and bright the LED. So we're going to copy this function as a start, the timer frequency, and modify it to be a PWM function. And we're going to set everything up in this function, so it's going to be a void, and we will call it from main. Now, the first thing we want is we want the PWM frequency and resolution to be as high as possible. That means we don't want any prescalers. So going to the data sheet and looking at the register description, we can see that to remove the prescaler, we want to write to CS10 as opposed to CS12. What we're going to do is use one output compare interrupt to turn on the LED and another to turn it off. And there's a channel B as well. Our frequency is, now we're using a prescaler of 1. Well, if we have a look at the equations that we used before, well, just rearranging the equation to figure out what value for the output compare register A in order to generate a 10 kilohertz sample. We have a CPU frequency of 16 megahertz, dividing by 10 kilohertz times 2 is 800. That's our output compare register A. And output compare register 1B, if we set that to say 100, it'll be a duty cycle of 1/8. Now we must use this first interrupt vector as LED on and set up a second vector, but now Alt G to go to the definition using the compare B vector, but to turn the LED off. And we can see that the proportion here will represent the duty cycle. So let's run this and test. And ideally the LED will come on quite dimly. And if we had to change this to say 400, we should see a much brighter LED, which is the case. In the following video, we'll try and have a look at the specific waveforms and understanding a little bit more of the debugging tools that Atmel has to understand and read these frequencies.